to make acids. All those three fatty acids, they're acids. Acetate, propionate, acetate being vinegar. So acetate, propionate, and butyrate, they will decrease the room pH. And if that room pH gets too low, it's going to kill the bugs. Okay? Your point's an interesting one, because if I change what I'm feeding my cow, I'm feeding it starch, or I'm feeding it hay, which is really fibrous, more cellulose, there's two different populations of bugs in there, just like your GI tract. Well, the bugs in your hind gut are dependent upon your diet. They're going to change. And in that cow, if I've been wintering a cow in a feedlot on a high roughage diet, and now I want to move it on to a high concentrate diet so that it's getting more digestible energy, more metabolizable energy, so I can increase its growth rate. I've got to do that slowly. It takes me about 3 weeks to move from a high fiber diet to a high concentrate diet because the bugs change. And then because the bugs with the starch are going to be we're going to have a little lower pH, and the way they metabolize it will be a little different. So it's an interesting question. There's a whole series of things going on in your gut. We spend a lot of time with the pig worm looking at various things you eat and what it does to the microbiome in the GI tract. They have a lot of implications for health and disease. So I spend a lot of time with the pig worm getting poop samples of graduates who were breaking with their arm up a big poop. Great way to get a paper. What'd you do? What'd you contribute to your scientific sample? Well, I reached up. Okay, what else? Oh, glucocorticoids. So I think I said one day that I sort of think about life as having two hormones. We have an anabolic hormone, and we said that's insulin. You increase insulin, you increase fat synthesis, you increase glycogen synthesis, you increase protein synthesis. If you decrease insulin and you increase glucagon, you increase glycogen degradation, you increase gluconeogenesis, you increase fat degradation, and you increase protein degradation. Those two hormones are peptide hormones. They're protein hormones. We also have steroid hormones, and I don't need to leave them out. But glucocorticoids, when they go up, they're number one made by adrenal cortex, and they're also made by adipose tissue. As those go up, that's going to increase gluconeogenesis. So glucocorticoids are going to play a role, but we'll get to that. We'll get to that sooner or later. Anything else? Epinephrine. Epinephrine just increases liver glycogenolysis in the muscle, but you know why, so I don't think there's much to say there. I think we're there for gluconeogenesis. We'll talk more about it in terms of controls, and we're going to talk about type 2, type 1 diabetics, and metabolic syndrome in relation to all of this a little later. But I want to we got to do adipose to get there. So I've got one more pathway to do, and that pathway is the pentose phosphate pathway, but I'm not going to start it today. I'm going to give that to you. But what I am going to start today, and finish, is fructose metabolism. You have time? Yeah, we got 30 fructose metabolism. Fructose. You've got two basic sources of fructose in your diet. One is going to be sucrose. And you recognize from previous structures that sucrose is nothing more than a glucose to a fructose, and they're hooked together in an alpha 1 to 2 linkage. Alpha 1 off the glucose to the alpha 2 on the fructose. And so we digest that with sucrase, and we absorb the glucose by SLGT1, and we're going to absorb the fructose by G5.
The primary other source is going to be from high fructose corn syrups, which really, when you get right down to it, are high in fructose. But high fructose corn syrup is made by breaking down cornstarch to glucose, and once they convert the starch to glucose, they treat that glucose with glucose isomerase, or sometimes called isomerase, and that glucose isomerase makes fructose, and what you get out of that deal is a high fructose corn syrup that's about 90% fructose. They take that high fructose corn syrup that's 90% fructose and they mix it with glucose. So they're going to add glucose to this, and basically on the market there's two types of high fructose corn syrup. One high fructose corn syrup is 55 and the other is 42. So we end up with high fructose corn syrup 55, which is 55% fructose, high fructose corn syrup that is 42, i.e. 42% fructose. And then they use that in processes. There is a third source, and that's, I almost can't say it. It's fructose. But it's natural. It's natural. It's in honey. What the hell is unnatural about that? I spent 6 years of my life on a sugar beet cover full of sugar beets out of the ground so we can make sugar out of it. Right there in the sugar cane. Don't buy that stuff. Sugar beets are better. So that's what bought me a car, sugar beets. So those are the sources. Metabolism. That's the key buy for us. It's not very regulated. Number one, it's transported in Glu-5. That's not regulated. Okay, there's Glu-5 on the cell surface of the enterocyte, so that's how you absorb it into the enterocyte. You dump it out of the enterocyte usually with the Glu-2 in the red into the blood. But then you have Glu-5s on all the tissues, and so it's really not regulated. So the fructose is transported into cells in an unregulated fashion, all the cells. So that's an issue. So there's no insulin required. Pretty much, we're going to find that fructose tends to be metabolized in the liver. We tend to metabolize fructose in the liver. Now, hexokinases, 1, 2, 3, and 4. Hexokinases have the ability to produce fructose 6-phosphate. So we can use the hexokinases 1, 2, 3, and 4 to make fructose 6-phosphate. There's stuff in the literature that says that the hexokinase form in the liver has a pretty high Km for fructose. But also in the liver, there's another enzyme, and that's fructokinase. So liver has fructokinase. And fructokinase takes fructose, I won't bother with structure because you're wrong, fructose plus ATP, it's going to make fructose 1-phosphate plus ADP. So rather than getting fructose 6-phosphate, we're going to get fructose 1-phosphate. The hexokinase has a really low K, or the fructokinase has a low Km, has a low Km for fructose. So it appears that most of the fructose that you consume is going to be converted to fructose 1-phosphate. Very little of it is converted to fructose 6-phosphate. Well, here we are in the liver. The first thing we're doing is we're rapidly converting, if you had some high fructose thing in your diet, we're rapidly converting that fructose to fructose 1-phosphate and ADP. You might go back the last quarter and remember, fructose 1-phosphate is actually going to control glucose metabolism. Because fructose 1-phosphate, if you look at the nucleus of the cell, in fructose 1-phosphate, in the nucleus of that liver cell, we have the glucose regulatory protein, and that binds glucose. And so you have glucose coming in and binding, and that is facilitated by fructose 6-phosphate. So if that gets up, it starts getting high, we're going to start to bind up, this is the glucokinase regulatory protein. I should put K in there. So that's going to inhibit glucokinase. Glucokinase regulatory protein in the presence of glucose. And fructose 6-phosphate, we're going to bind the hexokinase. Way ahead on myself. You bind the hexokinase 4. It's inactive. So fructose 6-phosphate slows down correlation with glucose to glucose 6-phosphate as fructose 6-phosphate builds up by binding up the hexokinase 4 with the glucokinase regulatory protein. You got fructose though. You ate fructose, and now you got high levels of fructose 1-phosphate. That fructose 1-phosphate goes into the nucleus, and it's responsible for increasing the release of it results in the release of hexokinase 4. Consume fructose, it hits the liver, it's converted to fructose 1-phosphate. Fructose 1-phosphate tends to keep high levels of hexokinase 4 out in the liver cytosol. That's going to increase the metabolism of glucose. So fructose 1-phosphate, consuming fructose 1-phosphate, consuming fructose with the production of fructose 1-phosphate is going to increase the degradation of glucose. You're going to more rapidly degrade glucose when you consume fructose. You're going to slow down that degradation if you're consuming something like starch that has no fructose in it. Consuming fructose is going to increase the rate at which you convert glucose to pyruvate. Okay? So that's one thing. Second thing about fructose 1-phosphate. So we've done metabolism of glucose to glucose 6, glucose 6 to fructose 6, to fructose 1,6 to phosphate. That fructose 6 to fructose 1,6 to fructose 1,6 to fructose 6, that's highly regulated. Fructose 1-phosphate, there's an aldolase B, and it's going to convert fructose 1-phosphate to dihydroxyacetone phosphate and glyceraldehyde. And here, we're going to have to do something because we only have 1 phosphate on there. Oh, and that should tell you, if I ever ask you on an exam to label the carbons that come from glucose that are on dihydroxyacetone phosphate and glyceraldehyde 3-phosphate, now you know. Fructose 1-phosphate makes dihydroxyacetone phosphate. So this has got carbons number 1, 2, and 3. This has got carbons number 4, 5, and 6 off of that glucose. We need a glyceraldehyde kinase, so we're going to use a kinase, ATP. So here's our second ATP kind, ADP, and we'll make a glyceraldehyde 3-phosphate. And that's the story. From there on, it's pretty much the same. Except there's some highlights that you should know. One is that we know that the way we're metabolizing fructose is by using fructokinase. So we have fructose that you have absorbed into the liver, and without wasting time with the structure of that fructose, in the presence of fructokinase, And an ATP is converted to fructose 1-phosphate, and ADP, you know right away that the fructose 1-phosphate in the liver is going to increase hexokinase 4 activity. The fructose 1-phosphate is converted to dihydroxyacetylene phosphate, aglyceraldehyde, and we can phosphorylate that glyceraldehyde with the glyceraldehyde kinase, so we can get the 3, and that's going to take an ATP. So we're still going to get a glyceraldehyde 3-phosphate and dihydroxyacetylene phosphate. It's still going to cost us 2 ATPs to get there. There are a couple of fructose hereditary diseases related to fructose. The first one is you can have what's known as hereditary fructose intolerance. With hereditary fructose intolerance, you're intolerant to fructose. Hereditary fructose intolerance is aldolase B deficiency. Aldolase B. This usually shows up in symptoms, usually just about the time you leave them. That should tell you something about what you might be feeding an infant when you wean the infant. You're feeding it something that has fructose in it. And what happens is fructose 1-phosphate builds up and there's diarrhea and vomiting. This makes them a sick little infant. So they don't deal well with that at all. So solution to the problem is keep them off fructose. Don't feed them anything that has fructose in it. They're better off without it anyhow. We'd all be better off if we didn't have fructose. The second one is essential fructoseuria. This one's not bad. In this case, there's fructose in the urine, and what we have is a deficiency of fructokinase. And there's really not much problem with this one. I mean, ultimately, you don't want hexoses going through the kidney. You don't want to be peeing out sugars, not good for the kidney. But aside from that, there's no real negative consequence of this. And again, the thing to do is just feed a diet that's free of fructose. So those are key buys. Yep. The fructokinase. It's a deficiency in fructokinase. That's why it's essential fructoseuria, because fructose builds up. So we've got 2 diseases. One in which fructose builds up and just pee it out. One in which fructose 1-phosphate builds up. And there's a lot of consequences to that. I mean, the consequences of this disease are pretty bad, because what happens is, how are you making that fructose 1-phosphate? You're taking ATP to ADP. You haven't got a whole ton of inorganic phosphate hanging around the body being used that you can use to remake ATP. You're going to start precipitating an ATP deficiency because you got so damn much phosphate tied up in that fructose. That fructose 1-phosphate doesn't go anywhere. You're not going to get that phosphate back. With glucose 6-phosphate, fructose 6-phosphate, fructose 1,6, we get those phosphates back. In fact, we make ATPs out of it by substrate level phosphorylation. Here, you've got that phosphate tied up. On top of that, the poor old liver has with the hexokinase regulatory protein, the glucokinase regulatory protein, that's devoid of any glucokinase, hexokinase on it. So glucose metabolism is proceeding at hell-bent for election, and you can end up with lactic acidosis as a result, because you're running that glucose through so fast. Okay, so those are the diseases. Yes. This one? That one? That's hereditary fructose intolerance. HFI, hereditary fructose intolerance. So these people are intolerant to fructose. These people are not intolerant, but you don't need to be eating fructose and running fructose through their kidney. That's not really the best thing to do with a kidney. The bigger issue with fructose is the rate of metabolism. So that's what we have to look at. So your sources of fructose are going to be sucrose, high fructose corn syrup. both of which the sucrose is degraded in a hot second. So it's going to be converted to glucose and fructose in a hot second. The rest of the fructose is already free. It's going to be transported through GLUT5, and it will be transported rapidly in the enterocyte. It will be transported rapidly out of the enterocyte into the blood. Into the blood, it's going to show up in the liver, and in the liver, it's going to go from fructose to fructose 1-phosphate, dihydroxyethylene phosphate, and we're going to make glyceraldehyde 3-phosphate. Bear in mind that DHAP is also able to make glyceraldehyde 3-phosphate because we have the triphosphate isomerase. Guess what we just did? We bypassed insulin and glucagon control at fructose, making fructose 6 to fructose 1,6. We bypassed PFK fructose 1,6 bisphosphate control. That regulates the rate of glucose pyruvate. This is not regulated. It's going to go to pyruvate, and it's going to do it in a hurry. Some of the consequences of that. One is that you're going to start running out of NAD to make NADH, a glyceraldehyde 3-phosphate dehydrogenase, so you're going to have to convert pyruvate to lactate. So you're going to start increasing lactic acid production because the fructose is metabolized so fast. Second thing that's going to happen, that pyruvate, you're making a lot of it in a hurry, and it's going into the mitochondria. It's going to be converted to acetyl-CoA. There's going to be a lot of it there because there's not much regulation taking place. That acetyl-CoA is going to enter the PCA cycle. All of a sudden, ATP to ADP is going to go up. NADH to NAD is going to go up. And those two controls are going to shut down the PCA cycle. Citrate is going to build up. It's going to come out of the mitochondria into the cytosol, and now you're going to increase MAP synthesis. So if I feed a rat fructose versus glucose, I'm going to see a rapid rise in circulating fat in that rat. If I feed them sucrose, it's kind of an intermediate rise. So I can regulate the amount of fat during absorption and metabolism in that rat blood by feeding the glucose versus sucrose versus fructose. Because the fructose is going to be very lipogenic. And it does it because it bypasses all these controls. We'll pick up the last.